All right, today's sponsor is FMS Sign Products. FMS has been providing quality products for neon sign industry since 1946 and strives to support the tube benders by making it easy and quick to purchase the materials they need. FMS offers a wide variety of readily available and competitively priced products, which can be purchased directly from their easy-to-use website. Don't need a whole box of tubing for your project? No problem. FMS can ship partial boxes and mix and match colors and sizes as needed. Shipping is secure and easy anywhere in the nation. Check out their website at fmsneon.com for a full line of products and see how easy it is for all your neon supplies to be shipped directly to your door. Again, visit fmsneon.com. That's fmsneon.com for all your neon needs, and use the promo code LIGHTNING at checkout to save 10% on your first order. Now, this may just be more than just your first order. There'll be a couple things that's going to be in today's slides that I think this, is helpful for you to cut off some of your costs when you're purchasing your supplies for your neon business, or you're a student or educator, or maybe you're someone like myself who's dabbling and exploring plasma as an art form, which are soft glass materials. If you're looking for electrodes for borosilicate, then look for me at taminglightning.net/store, where I have borosilicate electrodes for 12 millimeter and 16 mil. So again, welcome to the Chapter Notes Plasma Primer live stream. This will be the last of what I've prepared for January, where I was going over guides that I've pretty much been inspired by the Enter the Plasma collaboration with GEEX. Most of what we're talking about is within the realm of Chapter 2. Chapter 3 is something I'm still trying to put together in a succinct way, and so I do hope that this series is very helpful for anyone who is, have known that I put out these guides that I've used in my classes, but also may have some difficulties with reading. I've had various students reach out to me to say that they appreciate having me go over the lectures and slides. It also allows me to kind of impart more than what I can actually put on the screen. But for those who have difficulty with reading, sometimes having an audio format is very helpful. So this is also part of that, to kind of make sure it gets out there in as many different formats as possible. And I hope to continue to improve as I do more of these presentations and perform more of these live streams. And of course, the live stream here is an opportunity for anyone to ask questions during the stream that will allow us to kind of address things in a moment, because there's always something I'm missing when I put out these presentations or perform them, and the live feedback or even post stream feedback and questions is helpful to inform me and improve the content, or improve answering questions that people might have, so that I learn a lot from that myself. I'm going to move myself out of this, out of the way here, because most of the presentation will have the full screen. So I'm going to kind of disappear slightly right now. So in today's live stream, we're going over the guidelines for vessel structure, or the plasma vessels guidelines, or plasma structure guidelines. And this is sort of the second edition of me reiterating the presentation and the slides. So this is sort of an idea of understanding what it is about plasma that we have to be concerned about when we're creating our glass vessels. The thing that contains the gases, the sculptural hollow objects that we are designing that will be illuminated. And to start out, it's very important to sort of understand what is structure and its relationship to vacuum. So what I've done, just like in Chapter 2 of Enter the Plasma, is kind of try to put out very succinct, very clear definitions to help us just grasp the very basics of what's to be understood here. So structure is to support an object or a load, and that load is atmospheric pressure. Pressure is the force that is created when atoms, molecules, or particles strike the walls of their container. when we talk about the states of matter, we're talking about a change in the energy that that matter has. It's a shift, a transition between energy states. If you heat up ice, which is a solid water becomes liquid water, and it has its own properties. It's kind of stuck together, and it has a finite, has a certain level of volume compared to its container, and it takes the shape of that container. You add more energy to water, you get steam or water vapor, and that's a gas. And that gas is a high energy state of matter. It's bouncing around, it's filling the volume of the container regardless of the actual amount of particles. And that gas, when gone up to the next level, whether it's heat or using microwaves or using high frequency waves or electricity, jumps it up to another state, which is a pool of charged particles, in which it starts to where it attempts to maintain a level of normalcy through releasing heat and light. And because we're constantly feeding it energy, it's going to continue to release heat and light. So when we're thinking about something like vacuum, we're thinking about how the pressure is different from the inside compared to the outside. And that outside pressure, we're just going to simply say, for simplicity's sake, it's atmospheric pressure. And this is important because we're talking about how the pressure is being exerted on the glass object. If we have, and maybe this is something I need to add because this is something that I have just thought of right now, is you have a cup or container and it has an open end. It could be a closed form object. There's air molecules bouncing on the outside and there's air molecules bouncing on the inside. And when you change the air from inside the object and remove it, you are disproportionately applying pressure or force to that structure of the glass. And this is why your structure is very important. And there's a potential for failure here. So what happens if the structure fails? And warning for those who might have some like, I guess, a sort of trigger warning for those who don't like a lot of violent things. Now, there's not going to be any harm in the next slide or video, but it is quite an expression of violence when something implodes, because an implosion is the risk of failure. And what I appreciate is that there was a video that showed us this implosion with a high-speed camera. So we have a slow-mo camera, and this is done by the Beyond the Press channel on YouTube, where they were asking, will scratch glass on a vacuum chamber implode? Now, the end result is they had to kind of throw a battery at this object in order to get it to implode. But that was a situation in which the form, the shape of the glass, had given it so much strength that regardless of scratching it, regardless of cracking it, there wasn't enough structural weakness for it to implode on its own. And so it needed a little bit of help to throw a battery at it. And let me just show you this video real quick so you can understand the violence of an implosion. It's very quick. Glass becomes dust and particles. The danger of an implosion is that it's an instance of collapsing of violently inwards. And it has so much energy that those particles of glass and dust pass each other and eventually becomes an explosion. Because you created a vacuum, the rush of air is going to fill the space that the vacuum displaced, which was the form the vessel was containing. And again, the danger of this is that it has enough force that it becomes explosive, and those fragments can be harmful. Very, very awesome video. I really like that we have that available. There's been a lot of other channels that have tried to go ahead and try to, explain this or show it, but they weren't using the right equipment, so it was not enough of an impact to understand. An instantaneous explosion, sure, shows you how violent that is, but I wanted to make sure I could show people the way that the object breaks, which is just as important visually as information. Let me just try to move to our next slide here. So now that we have that out of the way, yes, implosions are dangerous, but there's a lot we can do to prevent or mitigate or reduce these issues with proper inspection and structure. And luckily, there's a very few moments when implosions can actually occur. So your prevention and mitigation is how you reduce the risk of failure. An object breaking under the change in displacing of vacuum or atmospheric pressure on the object. So there are sort of three instances I can sort of categorize here of where an implosion can occur. One is during the pump down or evacuation of a piece, where it's being a vacuum being pulled on the object. Now, this is preventable by proper structural design and execution and inspection. This is also mitigated by creating a barrier, standing offline from the object or vessel, and wearing the proper PPE, such as safety glasses. So if this thing does break, we have a barrier over the object or between us and the object, and we are standing not in line with the object at all, whether behind or front, and we are wearing safety glasses. When I'm working in class, I emphasize safety glasses a lot. And I will not make the next step until everyone in the vicinity has safety glasses on. Number two, this is post-fill, such as being broken by impact or drop, meaning that someone's broken the object after it's been filled. So this can be mitigated. You really can't prevent it other than making sure no one drops stuff on it or handles it improperly, but accidents and incidental aspects do happen. So you can mitigate that by adjusting your fill pressure relative to the scale or volume of the vessel. And this is sort of a little ambiguous, and that's because there really hasn't been, for me, and for everyone else out here, a sort of study on this. Ideally, the more space you take up, the bigger the boom, I should say. So in this case, it's suggested that less volume that is being displaced, the less energy when it breaks. But I've seen smaller objects basically implode quite violently, and almost like someone popped a balloon in terms of volume right next to your ear. And I've had instances of those. So I think one of the tips that's been given to me is by Mundy Hepburn, who says a good tip is to fill at least a quarter atmosphere or safer half atmosphere, again, relative to your end result, relative to the scale of the volume of an object. Mundy has made pieces that are larger than watermelons and 6 feet long and have big bellies of shapes and things of that sort. And those can impart a lot of force because it's displacing a lot of volume. But you can still get similar glow discharge effects at quarter atmosphere relative, again, to your volume or your shape or your end result you're looking for. The idea here is if you're going to go big, be as safe as possible, but do not compromise your aesthetic concerns, because there's never going to be a space where everything is off as safe as possible. We drive cars that are quite still safe, but then quite still dangerous in context. So we just want people to make objects that are strong structurally, and we want to make sure that they are put in a position in which they are not going to be a failure being falling over or someone dropping something on it. So things that are obviously can be removed from being an incidental scene. So this can be, again, the third aspect is this thing could be a piece of compromised glass, such as having a foreign inclusion, improper annealing, or defect. So this is, again, preventable by proper inspection. And I sort of have to say it this way because what we're looking at right now is, you have an incident where it could pop while being evacuated. You have an incident where this can be broken after the fact has been filled and set up the display. And you have an incident where this can break because there was some sort of defect in the glass or improper annealing, which can just happen if you're not going through everything as proper as possible. And I do have a story down the line, so I hope that can get to us pretty quickly here. So my guidelines are about 6 different points, and some of these don't exactly attribute themselves to being directly related to the structure itself. And those guidelines for vessel structure are ensuring proper seals, closures, and welds, having adequate wall thickness, making sure that object is round, or a part of your design is round is good. You want to avoid large flat surfaces, and you want to check for imperfections, scratches, and foreign inclusions in your glass. And then lastly, which should be a part of your whole practice as a glass artist in general, is watching out for stress and compatibility in your vessel. Now, several of these are things that you have a lot of control over, and once we get to those, I can go into that in a little more detail. So by ensuring you have proper seals and closures and welds, you have an object that can be evacuated. This is not going to be a moment where the object is going to implode because it has an improper seal or a bad weld or closure. It just means it's not going to be viable to be evacuated in the first place. And this is one of the most common issues that we run into when we're troubleshooting when making our plasma vessels. So these improper seals lead to tiny holes or gaps in your object. And this is aside from the intentional electrode or tubulation that you put on the object. And this will lead to, again, a very weak vacuum, an unsealable, and then by nature, an unpumpable piece. And what I have here is a slight example of what a leak looks like and what you would use to find that leak. Again, I think there's a lot that I could put out there to help us, and I think there's a lot the community can help contribute too. But one of the tools we use to check for leaks is we pull an object under vacuum. We check for, again, the vacuum rating on the gauge. But if we see it's not coming down as fast or it's not coming down as deeply under vacuum, we'll check using a spark coil. And a spark coil will be a way to sort of pinpoint most leaks. And what we see in this image here is a slight white dot. We're seeing that as we bring the spark coil near the leak, it finds the little tunneling of inside the glass. And this is while it looks beautiful, this weld might have had some dust or dirt or a thin section while I was putting together. And so all I had to do was clean the surface of that glass and then melt it with the torch and work it. Now this is borosilicate glass, and that task is so much more of a probability and more capable of an action. Now you could do this with soft glass, but there's only very few options you have, and when you do that, you have to commit a lot to the setup to do that fix. When I tell people oftentimes as students, they'll be like, well, Percy, like, you're telling me we can't fix it if it's soft glass? And I'm saying it's not that you can't, is that you have to think about, and this is often students who are still in school, I give them an example that says, when I'm renting the studio, it's $35 just to have the hole. It's $10 an hour for the annealer or kiln I'm using. And if I'm using any tools from the studio, it adds up. And so if I'm spending hours of time for that one piece, I might as well do a batch of them at a time and make sure I can utilize that time and that equipment very efficiently. There are workarounds, there are methods to recover, but most often, if you're working in soft glass, you just have to do the task again. And I've broken many pieces from mishaps and had leaks happen from pieces that couldn't be fixed in a normal way. And then the abnormal way just means it's on a waiting list to fix. You want to have adequate wall thickness. Now, this is one of the ways that you can really influence the structure of your glass. This is something that comes with developing your artistic practice and developing your craft in the material that you're working with, which is glass. The more you get used to working with that material, the more you control the thickness, the more you get the right amount of material and move it around, the better you will be able to get this down. We could say that it doesn't really have to be terribly thick to be strong. But the idea is you don't want to have any flex in your glass. And you want to make sure that you're not overstretching the material that you have. Scale is everything in this as well. So if you make an object way bigger and big and thin, then it's going to not be as strong as if it was smaller and thicker. So you're better to err on the side of making the glass much thicker. And again, the way that you form or shape the glass can affect the integrity of that thickness. Round is good. It's no coincidence that a light bulb is shaped the way it is, as it is the archetype for the structural shape. A circle, for example, is a mirrored arch, and a tube is an extrusion of that circle. And by rotation, a circle becomes a sphere capable of redistributing force evenly. And one of the things I've sort of gotten from Ed, and this is how Ed teaches, he sort of likes to provide rules or like ratios to give us an understanding. He's worked in architecture, so some of this may come from his architectural design background. And he always gives us enough information that we have a margin of error. So his suggestion is that if you have sort of a concave surface or a convex surface, a concave surface is a surface that is bulging out, a convex bulging in. And what you want to avoid is having a too shallow of a surface that it becomes a flat surface. Because the reason why we have this roundness in the glass is it imparts a distribution of force. It's a stronger structure. So if you really need to dig into measuring this in some ways in part of your design, then it is a 1 depth to 10 length rule for your convex or concave surfaces. So depth, meaning how much the bulge is out. Length, how the length of the bulge is on your object. So an example would be the pieces I've been doing with Daria Sandberg, where I have these cloud pieces. So again, you want to be able to make sure you can distribute that force as evenly as possible. You want to avoid large flat surfaces. And the reason why is that the surface will not equally distribute the weight of the atmosphere. And I know that I can't stop people from doing this, so I want to make sure I can give people something that they can work on if they want to, if they dare, or, to have a large flat surface, they have to proceed with caution. If we're looking at this example here of the table, the force is going to distribute on the junction that's unsupported, which is a large flat surface. The edges of an object are supported by other structures, and that's why you don't want to have large flat surfaces in the case of implosion. So the exception that we're going to use, again, from Ed Kirshner is sort of this using to modify your thickness. You can have large flat surfaces, but you got to move that thickness. You got to train that thickness in the glass making process, which is a 1 thickness to 20 length. So if you have a certain length of a surface across, then you want to make it thick comparatively. And I think I do have an example here of some pieces here from the Ed uses. So Ed has done something where he's he's had these cylinders made. They're 5 inches diameter, and so it has a 5-inch wide surface, and therefore through using some of the math here, which I hope I have in this example here, the person who was making for him had to make the object at least a 1/4 inch thick at the flat surfaces to support atmospheric pressure so that the glass doesn't break. This is something I want to do more research on. I'm hoping that I can get some funding and sort out where I would do some of these studies, because I know that companies like Vitro, who are supporting the Pittsburgh Glass Center, I know companies that produce various glasses for architecture design have that in their proprietary sometimes, especially Vitro's VacSeal product, which is being used in the building for the Pittsburgh Glass Center. I do know a few people who are tangential or actually work at Vitro, so I'm hoping that I can find that way to use some of these different contexts to to explore more of that, because I think that could be valuable. In the end, I just still think you should avoid large flat surfaces. We have something like the geometric study that was done in collaboration with John Sharvin, and these are about 3 inches. And I think, I wasn't even thinking very strongly about that, but we tried it anyways. I mean, we put up barriers, we shielded ourselves, and it worked out well. These are quite, the smaller section is quite small. It's like the small size of like an ornament. The larger one's like kind of like a kid's soccer ball. And sort of what you're looking at here is you're creating smaller surfaces, sure, but there's something about the geometric or geodesic dome shapes that are helping strengthen this object as a whole. So you can use geometry and structural design to enhance the structure of the glass itself. While this isn't as, terribly, it could have been much thicker to give it much more strength and integrity. Then there's works called like lumen glass, which is invented by Wayne Stratman. We have some examples here, our collaborations with Mark Ditzler. We are teaching a class that works in this principle at the Pittsburgh Glass Center this year. I still think there's 3 seats left for the summer. If this is a class you're interested in, no glass experience needed. We go through a lot of different ways of using flat glass to create these vessels for plasma, but also some of the things we do can be new ideas that you can apply to your glass practice, especially the soldering of the glass electrode onto the piece. So again, aluminum glass invented by Wayne Stratman. It creates these flat glass panels that are supported by glass beads or have some sort of internal surface structures or pillars built within it. That's how these large flat surfaces work in these particular pieces, where you can see there's channels, meaning it has support structures. Like when you have a building, there's pillars that support the roof of the building itself. And another thing here, which my brain's not working right now for a second. Sorry. Pillars. Yep. So what you could do here is you could do a lot of different things to give that strength. And this is sort of what we'll be exploring in the class this summer with Mark Ditzler at the Pittsburgh Glass Center. I thought there was something else I wanted to add, but I don't think I have that in mind right now. So checking for imperfections, scratches, or foreign inclusions in your glass. When I was working with Dr. Jen Figg and Matthew McCormick, we were doing a project where they were making these glass drops that were then lit by LEDs. And the reason, this is sort of what I picked up from working with them, is that you can't just say you can get away with having a piece of stuff in there, or you saw that there wasn't a lot of stress there. The second you do that, you are now liable because you made a note that this existed. And ignorance isn't going to save you either, so you always want to check the surface of your glass. You want to check if there's imperfections. If you can, make sure you check for stress, which is sort of the next slide, and compatibility. It's just that if it's in your glass and it shouldn't be there, don't use it. And I've seen people talk about this in borosilicate, where opals can kind of made to be stay within the object, but they're not compatible. They made it a way so they coexist. The second you add extra stresses onto the glass beyond what you're kind of using as a decoration or a flourish to your sculpture or your pipe or whatever, you start to get in the realm where things are going to start to crack if there's a drastic change in stress through vacuum, or drastic change in stress through additional heat added from using a pipe or a bubbler or whatever. Again, I might be wrong in that description here, but it's all the same. You add extra variables when you do that. And again, you have to watch for stress and compatibility within your vessel. So spend the time to properly near your glass. Nothing comes of rushing. You're not going to save yourself money if you are constantly destroying all the time and money you spent making something. Of course, things will break because you're learning, but there's no need to rush proper annealing. You also want to make sure that you test your colors and glass types for their compatibility with each other. Even the process that I use for glass solder comes through tests. And if things aren't working together, I can't use it. And this is sometimes the matter of using different glasses or using ready-made objects to add to my structure. Because putting the glass under vacuum is the moment of truth. And sometimes if there's a problem, it's the best thing to do is to start again. It becomes very difficult to assess if you've done proper annealing. In the case that, like, if it's colored glass, you cannot see the stress in colored glass. I don't know anyone who has a tool that can do that. You can see it very easily in clear glass. And so in that case, what you should do, if you're not working in a private studio that you own and you're working in a public studio, talk to the studio managers, talk to the studio technicians, because they will, and from my experience, they will be happy to make sure that they work with you to make sure you have the right amount of annealing hours for your annealing. Oftentimes when I'm working on something and they look in there, they'll automatically ask me, personally, do you want to put on like a 24-hour, or this looks a bit thicker than stuff you like to use? And I think we could put you on a longer cycle here. You know, what do you think about that? Sometimes that initiation from them is really great, but I think you should also be part of that communication line and talking with the studio technicians, talking with the studio manager, and pay for that extended annealing cycle. It's worth it. And those are the guidelines for vessel structure: ensuring for proper seals, closures, and welds, adequate wall thickness, round is good, avoid large flat surfaces, check for imperfections, scratches, or foreign inclusions in your glass, and watch for stress and the compatibility in your glass vessel. Essentially, in this whole thing, these six points, there are five that you have to look out for. And there are 3 things that you can check, that you can control. You can control how thick the walls are. You can control how round it is. You can control how flat it is, right? Those are things that are within your control for your design. And then what's going to be part of your discipline and your integrity as an artist is checking for imperfections, scratches, foreign inclusions, and watching for stress and compatibility in your glass. Sometimes there are moments where things happen in the studio and it's improperly annealed. Sometimes that can be saved by additional processes in the way that you make the object. And I'm going to use a piece that I finished in 2021 to kind of help give context to that, if that should help us here in this situation. So I'm going to check here to see if there are any questions anyone might have. It doesn't look like anyone has questions so far. I can't quite see anything in the chat right now. I'm going to poke in here just for a moment. All right, so let's get back to, we have a question here. Jeremy Hayes, when enclosing metals inside a plasma piece, are there considerations, I'm going to pull my face cam up here. So Jeremy Hayes asks, when enclosing metals inside of a plasma piece, are there considerations if the metal off-gases? Okay, that's a good question. So yeah, the metal will off gas, but you want to choose a metal that is least likely to off gas and isn't affected by a lot of oxidation and the change in temperature. Sometimes metals, like if you're annealing a piece, which is at a temperature above 900 degrees Fahrenheit, the metals like copper will start to scale and flake off. Stainless steel is much more. It's much more sturdy and resilient to that. And then if you use something like nichrome inside your configuration, it's also very resilient to scaling and resilient to oxidation. And that's where you have to do a proper bake out when it comes to preparing your piece to be filled or pumped. It's the same reason why, if you're familiar with neon, that a neon tube is heated up by the bombarder. So that process of neon is common for a bombarder to be used. That's high voltage electricity traveling from electrode to electrode on a stick of neon tubing. And what that does, it heats up both the inside of the glass and it heats up the electrodes. This heat is going to remove the water vapor from the inside of the object as a neon tube, and it also will kind of scrub and clean that surface. It's one of the ways that you can clean the inside of that glass, and that gives you like your best possible surface. Now, there are techniques for neon that doesn't use a bombarder, which is a lot more gentle, right? And you can't use a bombarder with a plasma piece if I was making a piece at the furnace, because I don't have a point to draw the energy through the piece. So most commonly in the terms of plasma sculpture, plasma light sculpture, and if you even check out the episode on Taming Lightning with Tommy Gustafsson, which I think is episode 21 or 19, it's one of those episodes. He's using an oven or a kiln, so he's heating up the glass and heating up the air inside the glass tubing, which is the same thing that we do for plasma. We're using an oven like a kiln to heat up the glass surface and the inside, and that's helping us remove that water vapor, and it's helping us remove that from the inside of which includes any metal components on the inside as well. So you make sure that you are getting to the right temperature, and you're making sure that you are holding at that temperature long enough that everything inside gets hot before you evacuate. And that's how you can get most of that off-gassing removed from the metals itself. You also want to make sure the metals you have is clean, like you're not having any finger or oils on it. And I'm close to being able to write an article about that, and I'll kind of reference from Wayne Stratman's The Art of Plasma book and some of the references I found in other glass scientific books, like there's a Handbook of Glass Properties and Materials of High Vacuum Technology books on glass that helps me understand what the best ranges are, the ideal ranges are for heating up and baking out the glass to help with removing off-gassing. I hope that sort of answers your question, but that sort of topic has been on my mind for quite a bit as I've been doing my research in the books, and hopefully kind of helping explain that through all these different resources I've compiled over time. But that's a good question. I like that. So as I mentioned, I'm going to go through the making of Inspire Neon Citrus. I'm going to pull up the page here right now. So I'm going to use this piece as a way to explain how I work through my own artwork and the decision makings that have to be made to finish a piece. This is one of the least this is at least one of the pieces where I've been making more complex over time. And I think it kind of helps people understand how we apply some of these vessel structures to these guidelines to art making. So I make artwork that is inspired by which is the Spire series is inspired by what I start to carve out on the object. So I start with the lung and I make 2 lines and I start carving from it. And this was literally inspired by Ethan Stern and his work, where he showed me how he navigates carving his pieces and ways that he's done some unique stuff by doing his cold cut hot pieces or hot cut pieces, where he engraves, picks it back up as a grawl, blows, and fire polishes the surface before putting it away again. And that part of that process has been absorbed into what I do with my artwork now. And here's this hot cut series, an example of a piece that was a sort of a grawl blank of a piece that he blew up just a bit, carved into it, picked it back up, and reshaped it by changing it just slightly, either elongating or crisping up some parts of it. And so this is pretty fascinating thing, because it was sort of an eye-opener for me later on to approach this process again, because I made works where I didn't quite fire polish it. I wanted to polish it as much as I can with the equipment I had at the Pittsburgh Glass Center. And I find that this gave me my hands back for drawing, because I did not want to use my drawing as a sort of like an art practice. So you see this lung shape is where it started from, and I made several pieces like this, various combinations of layered color that I carved through. And I thought, well, now that I'm more comfortable with doing this process, and I'm more comfortable with pumping pieces for plasma, I thought I would extend into a deeper realm of combining these 2 things together, which adds a bit of complexity. I'm carving this piece, and then now I have to fire polish it. Now you're probably wondering, why would I fire polish this piece if I could polish it? The thing is, polishing is a different part of the process. Even though it makes it smooth, it's still, what polishing does on glass is it makes the rougher surface finer and finer and finer until it's smooth to your touch. But if you look under a microscope, there are peaks that eventually get rubbed down until it's so tiny that we get a smooth surface. And what we're not doing is we're not giving it back its integrity. It's not one surface again. So by fire polishing, we can then give back integrity to that surface, meaning that the outside surface becomes strong again. And even though glass breaks under tension, not compression, I still argue that it still makes the glass more brittle if the surface has some sort of scratch or sandblasting or engraving texture to it. So even though it's not going to break on the inside, there is a fragility to the overall structure. And that was something I had to really look for to get a sense of for the strength of glass. But this process takes a bit of time. I have to, again, not rush the process. I take these pieces that are at room temperature and I have to bring it up to just around annealing temperature before I bring it up to, which is around 900, 930, before I bring it up to 1100 for picking it up hot from a blowpipe or punty in the hot shop. So I'm using a hand torch to heat that glass and do it very softly and slowly, so that flashing of heat, so each time the person goes into the glory hole or the reheating chamber, they're bringing heat back into the glass, and then I get that nice smooth surface that I'm looking for. It's sort of a cheat in some aspects, but you really have to put in the time to make sure that you have as smooth and consistent surface as possible, and you're going to rely on your assistant to have another perspective. Maybe you missed a section that wasn't quite polished up. So it's a thing that you really can't do by yourself, because you need those different perspectives while working. So once I had the vessel polished, fire polished, and annealed, I'm even more sure of the annealing of this piece now that I've let it go through again. I have to go through the cold shop again. And aesthetically, cutting the outside shell envelope of the glass envelope around the electrode allows me to reduce that protrusion on the glass object. so I can insert the electrode shell further into the piece. And that's because if you guys checked out the design theory for plasma sculpture, this piece is like an object, and it's not linear in any fashion. So that extra 3 inches off the end just becomes a leverage point, an arm sticking out the car type of situation where it's more easily broken. But this also allows me to make this object more compact and find more interesting solutions. So again, the electrode here in this case acts as the conductor for charging electrical charge to illuminate the sculpture from the transformer to the gases inside. So it makes it a very easy way to do it. And by using that electrode, which is still readily available, I basically give myself a shortcut step to apply plasma to this object. You can see here that I'm using the process that I am quite a fan of here, which is using a glass solder. And we're using here is like a low fire enamel from Rouchet and a mixture of isopropyl alcohol to create a mixture that when heated in the kiln becomes vitreous and seals the 2 pieces of glass together. And I've become pretty much a fanatic of this application because it gives me the most control. I can focus entirely on sculpting the glass as part of the making process, engraving and fire polishing, without having to worry about this electrode sticking off the end somewhere. And then if I'm intentional, I could set myself up to successfully add the electrode in a separate process. By splitting up those 2 different dynamics, I can give my best to every step of the process. And this is something I learned from Ed Kirshner and continue to try to develop and understand and share with other people. And it's awesome that other people are doing it in ways that I've not yet done it, and in ways that they have learned before me, so that I can have a community of people that understand maybe the troubleshooting I go through, and we together can find new solutions, which is fantastic. Now, using a vacuum manifold is the next step. I'm hooking up the piece to the vacuum manifold. This is the sort of the current version that's sitting at the Pittsburgh Glass Center. And this is where the fun part starts. People want to get immediately to this part, but mind you, this probably took me nearly 20 hours to get to this spot. And I've actually had to fire this piece multiple times to get the seal to be correct, to complete the seal. So I've had to hook it up to the manifold at one point, evacuate it, see if there was a leak, and then add more solder on top to make it work. Currently, I haven't had to do it as much. I more likely have had to refire the piece of so the solder will flow again, which is pretty awesome. So, like, I understood that I wanted these 2 colors on the piece, and nowadays I have a better understanding of what my vocabulary is, so I can start to. Yeah, I think I did fire this piece maybe three times, and so when I'm looking at something like this, I kind of had to go to a recipe that I saw a while ago. So, like, sometimes you don't want to start from scratch, or so like a cook or wizard or witch, you rely on a cookbook, a grimoire, or a notebook to help you move things along. And there was a presentation from Carl Willis. He's got a YouTube channel. He's shown some of his mixtures. He's basically radiation safety is what his main sort of career path is related to. But he has started to dabble in doing plasma light sculpture with tubes and gas mixtures and vacuum systems, which is super awesome. And he had put out this presentation, and I started to look at the mixture, which was the neon nitrogen golden flame. And even in his notes, he stated that this mixture runs hot and that it is hard to light. So when I tried it out, I confirmed, yeah, he's correct. And I couldn't quite get the ratio between the gases he used, which was nitrogen and neon. Well, then Fortunate for me, I was able to call up Mundy Hepburn for some guidance, as he's had quite a deep history in mixing different gases. And he helped me refine the mixture by adding a pinch of krypton to the mixture. In short, how this works is that the nitrogen is that these different gases have a role. It's neon, nitrogen, and krypton. Nitrogen has to be used in such a small amount because it is a arc killer, meaning that it is very resistive, meaning it wants to absorb a lot of energy in order to exist as an arc, as a filament of light. So you want to use the tiniest amount of it. And what happens when it works with neon is it goes from the neon being red to like an orange or a peach color. And krypton itself does something unique here. So I don't have to have as much nitrogen if I have a pinch of krypton, because the krypton itself wants to form a line of light at a lower pressure of gas, which means the lower pressure that you have to work with before you add your other gases, the more efficient your mixture can be for expressing the energy being put into it, meaning I don't need as much energy to power the entire piece. I don't need a huge output. So if you know that krypton wants to form a filament at a lower pressure, we can add a lot less nitrogen and add a lot more neon. And we just keep adding neon after we get our tiny amount of nitrogen, our pinch of krypton, until we get our desired effect, because each vessel that you're working with will have a particular level of neon added to it that will look the way that you want it to. And sometimes there's forms that just don't work at all. But it was just that little guidance from Mundy helped me start to understand a little bit more about how these gases respond to each other and behave to each other and what roles they take in a mixture. And I'm hoping that I can reach out to my students again to get their notes, because their notes will kind of help me present a whole scope of different mixtures and how they affect various shapes. That's sort of the beauty of workshops, is an exploration of shape and exploration of gas mixture. So once I've settled into this mixture, which complements the colors I chose, the orange and the dandelion yellow, it was about finishing up the work. So I was designing sort of this protective collar for the electrode so so it's more resistant to being bumped or broken. And then the additional mounting hardware. If you look on the image on the left, you can see comparatively that this protrusion of the electrode is barely half as tall as the collar. That if I had just sealed a full tall electrode on it, it would have extended way longer than necessary. And it just showed you how well this works. But this took a lot of different research. How do I print an object that is strong with the least amount of material? It was about looking at how other people talked about structure, again, for 3D printing and 3D modeling. The type of shapes and geometries you add to an object to give it various new properties and strengths. So I was using 3D CAD software like Fusion 360 and printing and designing things that would fit together. A notch so I can line things up properly so it doesn't turn inside the socket. I'm also putting in holes that mount that hardware to my shadow box in a way that you don't see how the screws are added to the base. And the way that I kind of work through all this has been a combination of my contemporaries. My contemporaries are the sounding board to learn and solve a lot of my problems. And together we create this vocabulary that can help other people. So I used the PC7 epoxy as my adhesive of choice, as inspired by the international glass artist Harriet Swartzrock and her series of plasma hearts. And the use of 3D printing with plasma was encouraged initially by the artist known as Nerd Glass. That's N3RD, Nerd Glass. And then here's a quick little animation of how that collar fits into the mounting hardware. 3D printing allows a lot of customization. That means this object that is the mounting hardware could be changed. It could change the pitch of the object itself as whatever fits my series of Inspire pieces. Fortunately, a lot of them actually are the same pitch, so I don't have to do much modification for the hardware itself. By having sort of this ability to understand how the object comes together, and knowing that my solution is likely to be a shadow box, it was very easy to build around this concept. I made my piece, I made my mounting hardware, and now I got to make the thing that holds my electronics and allows me to display my artwork. And this is very challenging for a lot of people, because oftentimes we get to the point where we're just thinking about the glass object, and we just have this extra long appendage, or we have this weirdly placed electrode because we let go of what we knew because we're experiencing something new. I think there's a place for that, but I think we shouldn't run so headlong into a finished gallery ready artwork without really sitting down and discussing with ourselves and looking at our artwork and finding how to make that solution. So finding a solution for this piece was much easier because I had understood how to break up my artwork in order to make that complete. So making the shadow box allows me to protect the artwork from ambient lighting. If you check back with design theory, plasma doesn't often produce very bright light. There are small instances where you can get sort of that luminosity that can stand without any protection from ambient light. But in this case, for this piece, it needed that shadow box to protect it so that you can see it more clearly and effectively in a space that is well lit. And again, making sure the gallery doesn't provide any direct lighting. So again, I rely on my community talking about airflow and enclosures and getting critiques. And this is how critiques should be used. I think education doesn't use critiques very properly. As far as my experience, I think it's too early to ask to formulate a critique without having strict guidelines for it. When it could just have anyone's opinion, things need to be directed towards probably problem solving or things that are inclusive of the assignment. But here I was saying, hey, here's how I'm going to wire up my whole thing. Is there any suggestions you have for things that I'm missing? And he was talking, and Aaron was telling me it was about airflow. So one of the things you don't want in an enclosure is stagnant air, where dust can build up in a piece that has been sitting for a while in a gallery space. There's a potential for something to light up or spark, or just kind of, dust is not something you properly want in your electronics to function properly. So having airflow also gives this piece more longevity. The air pushes across the transformer, and then it exits through the top. The heat rises and exits the top and pushes out to the side. So I'm only separated from the wall by maybe just like 5 millimeters where these bumpers are, and that brings air from the outside, pushes it through across the piece from the inside, and exit through the top. And trying to find the best way to lay it out was quite challenging, but this is one of the ways that I could create this a very clean and accessible, which is very important, accessible space for your components. In the future, I think I would also, in the future, or at least lately, I replace these little sort of cleats with a sort of finger-locked cleat, so it can't move left or right if someone were to bump it or touch it. And additionally, I'll be adding a back plate so that if it's being handled, no one's grabbing and touching anything on the inside. But those are just considerations that come from making a piece and thinking deeper and further on the process. So again, the conditions of the gallery or room lighting is very important for being able to view your plasma piece. So it's not very bright. It's not as bright as neon. Neon's quite bright for the type of lighting it is. And so while you could display this in the gallery, having a shadow box is very important to be able to make that work very well. And if you look on the right side, same piece, we're seeing the how well that dark how well the shadow box helps, especially in a more intimate or darker lighting situation. This is where, in this situation here on the right side, this is where the gallery lights off, but then there's a big amount of light coming from the gallery opening, from the big old opening in the wall. So this is ideal, but you can't always expect a gallery to be able to turn off all the lights because that's a safety hazard for people walking around. But having the shadow box allows things to work very well. And boy, do the black 2.0 paint, it is amazing. Just in photograph, it barely shows up. It absorbs light in video. There's a thing about using the right color paints and types of paints in your process too. So if you have a shadow box, I would highly recommend the black 2.0. And if there's any other questions, let me know. And then if not, I can close up here shortly. I really enjoy doing these live streams. I think it helps people who may have some issues or trouble with reading, and sometimes it helps to be able to have someone explain and add little extra things as they work through a presentation. And every time I give a presentation, I'm often really getting new ideas as I walk through the information again. It looks like we have another question here. So when it comes to that mixture for the electrode, what temperature do you fire it in order to melt it? So the glass solder, and when I say glass solder, I'm going to emphasize that I am using a low fire enamel as a solder to attach the glass. There are industry standard, like industry designed solders or sealing glasses, but they are very difficult to get a hold of in reasonable quantities. And the company who was it? Faro company sells sealing glass for like CRT, vacuum tube type of stuff. But you can't get any less than 30 to 60 pounds. You can't get a sample size from them. So Ed had suggested using the Rouchet low fire enamel from his dozens and dozens of experiments. And that has been something we could use and has worked so far for me in the process. And that Rouchet, that low fire enamel, fires at 1050 degrees Fahrenheit. It's 1050 degrees Fahrenheit. And it suggests that you hold there for at least 15 minutes. And what I do is I get my piece coming up to my annealing temperature first and let it sit there and soak. Then I jump up to the firing temperature for the enamel, 1050, as fast as possible. And I hold there for 15 minutes, and I crash down to my annealing temperature as fast as possible, hold there for soak, and then anneal. That's what I do. I mean, it's sort of funny that they do call it low fire. but that's because other temperatures for this enamel, especially if you're doing glass blowing, if you look at some of the other glass blowing enamels, that's at a higher temperature where you'd have to use the glory hole or reheating chamber to fire it. You said there's a low fire enamel that fires at 2 to 400 degrees Fahrenheit. Which company sells that? And is it for glass or is it for ceramics? Well, that was the thing. So the reason why I jump up to the required annealing temperature instead of doing trade time for temperature is I found that it gives us a greater melt because it's not going to flow as much. So you could sit there and say, okay, I can hold at my annealing temperature for 4 hours, but I found that it wasn't flowing as strongly as if it went up to the firing temperature for the enamel, and have found that we had a greater success rate without any complication of mixing the soft flux with sodium nitrate and mixing it with lead oxide to lower that melting point. It was easier if we just went as straightforward as possible without complication, because you can always sort of dope or mix the Rouchet soft flux with something else and get there. But if you're just starting out, trying to teach someone to add the right amount of sodium nitrate and add the right amount of lead oxide was very challenging because, one, Ed would kind of know what he was doing, and then two, when I tried to break it down, there was a disagreement of order of operations, because the only way you can absorb break down the sodium nitrate is you need more water content in your mixture. So you have to use distilled water and then add a pinch of the sodium nitrate and then you mix in your low fire flux. Yeah, and I just found that if I can get up to that temperature, which again it's lower than the pickup temperature I would do, should be able to make that work for you. And if you're working with thicker glass, it's not going to move as much as that temperature range. And if you're not using a casting kiln, you're going to cool and heat faster. So you don't have you're not so there's still a lot of variables in there. Are you using a casting kiln? Are you using a front loader kiln? Is the kiln like a light? Is it built to hold the heat, or is it meant to lose heat quickly when needed? How thick is the piece? Um, how high does the heat actually overshoot in the kiln when it wants to reach proper temperature? Its cooling rate, so on and so forth. Um, it's like trading time for temperature is definitely an option. But if you don't have, you just have to make sure you're really good. You're really doing everything as clean as possible, because it's not going to want to fill or flow into gaps as easily. It brings us back to being intentional and being having a much sharper artistic practice. Definitely a lot more people joining this session than the previous ones. I'm happy about that. Really good questions tonight. Yeah, you're welcome. Yeah, please support the future guides and information. One of the ways you can do that is support on Patreon. You know, there's additional perks that come along with that. I'm building up more projects to release and share. Another way you can do it is just jumping on and subscribing to the newsletter. And just like what you're doing tonight, you've asked questions, and those questions are things I'm adding to my things to research and do more detail on. So questions, suggestions, and sharing is important here. So there's the QR code for the mailing list, or you can just go to taminglightning.net. But I'm really hoping the people come through to Patreon, because that gives me more power to bring you more things. All right. See you next time.